E passiamo allo speaker successivo, Ulrich Klotz del FEM, Germania. Il dottor Ulrich Klotz ha il titolo di Diploma Ingegnere in Metallurgia Fisica all'Università di Stoccarda e un dottorato di ricerca in Scienze sui materiali presso ETH a Zurigo, in Svizzera. È a capo del Dipartimento di Metallurgia Fisica presso l'Istituto di Ricerca sui Metalli Preziosi e della Chimica dei Metalli, il FEM appunto, a Schwäbisch Gmünd, in Germania. La sua memoria si intitola Leghe di Palladio 950 da microfusione a prestazioni superiori. Questa memoria parla di alcune nuove leghe di Palladio a titolo 950 con migliorate prestazioni di durezza, densità e colore, sviluppate a partire da studi di simulazioni termodinamiche con l'obiettivo specifico di migliorare le caratteristiche di microfusione. Prego.
Thank you very much for the introduction and for the possibility to give this presentation here. I will talk about the development of new palladium alloys for casting. I would like to start with the state of the art in palladium casting. Palladium casting is not so well known in jewelry industry because it's mainly a technical metal and there's not so much work has been done compared to silver, gold, or even to platinum. So when we develop new alloys with improved properties, which is the objective of this work, we first have to find suitable alloying elements. Then the investment casting process with palladium has some challenges which are different from gold or silver, more comparable to platinum. And then we selected, based on some trials, we selected some promising alloying compositions and produced new alloys in a quantity that were suitable for full-size casting in a production size trees. We investigated these new alloys in details and found some challenges. Some were known, some new challenges we encountered. So, as I mentioned, palladium is relatively new in the jewelry industry. It's maybe 10-15 years ago there were first studies by Teresa Freie on the casting of 950 palladium alloys. Then some years later there was a paper on the mechanical properties of palladium, and about 10 years ago there was a research project at FEM conducted by Jörg Fischer-Bühner at that time, who's my predecessor, where casting trials with many palladium alloys were conducted. Then the interest in palladium decreased a little bit, and it came up recently because palladium is always standing next to platinum. Platinum is well known, it's established, but palladium is, as I said, not very well known. And one point of with palladium is the relatively low hardness. We have a Vickers hardness of only 100 to 120 Vickers, which is a little bit too low for stone setting to hold diamonds or other stones firmly. And therefore there's always a risk of bending and distortion of such jewelry. But another issue is, as I said, the production point. Palladium is even more difficult to cast than platinum because it's even more reactive than platinum. And so you get the risk of porosity, what we heard this morning, shrinkage porosity or gas porosity in special. And there's also a risk of hot cracking. So this in general leads to quite high production costs, which might be even higher than for platinum, but at the same time the price of palladium, I have to say, was lower than for platinum, and of course the renommee of the alloy is not that high as for platinum. So the risk of in casting of palladium is demonstrated by some pictures here. So a completely broken casting tree where all parts are broken. You see in the metallographic cross-section they are full of cracks. In the cracks you see many dendrites, a picture you might know from this morning with these dendritic structures. And if you have a closer look here, you see these are these dendrite tips, and we measured the chemical composition here between the dendrites, and we found there are deep melting phases. The alloy has reacted in this particular case with investment material, and this resulted in a very strong embrittlement and complete fracture. So this is a risk in palladium, and such material cannot just simply be remelted and reused. It has to be sent for refining. So with this in mind and in background, we started the development of new alloys. And nowadays, computer technology allows to do a simulation of alloy compositions to determine the melting point or melting interval, the segregation of certain elements, that is, chemical changes during the solidification process. And also you get information about the reactivity of the melt or even age hardening. So with that you can save a lot of time and money and precious metal, because you can do many calculations and find out what are suitable alloying elements. Then we started working. We developed about 40 alloy compositions, were tested and made centrifugal casting and evaluated the most important parameters like the form filling, the surface quality, the porosity, of course, and the hardness, which was one of the key points. Our benchmark was always the most established alloy, which is 950 palladium ruthenium. Well, but if this alloy is established, why to do something new? The figure here I show here is the so-called phase diagram. The phase diagram shows the melting and solidification temperature of a mixture of alloys. So here you have, on the left side, you have pure palladium. On the right side, you have pure ruthenium. Our alloy is here, and you see this line here is the melting temperature, or exactly the melting interval. And such phase diagrams allow metallurgists to understand materials and their behavior. Now, our objective was to have a form filling and feeding and micro shrinkage which is at least comparable to 950 palladium ruthenium, but the hardness should be in the range of 130 to 160 Vickers, which is an established value for platinum alloys with good properties. This provides suitable stability. We also want to have a certain grain refinement to get fine grain structures which have more homogeneous properties and also higher hardness. Now, if you look in literature, you find diagrams like this. These diagrams show the hardness as a function of alloying composition. And now you see there are many possible alloying elements that have different effects on hardness. So for instance, if you add copper, the hardness increases along the blue line. So palladium is very soft, pure palladium with a hardness of below 50 Vickers, and copper has very little effect on hardening of palladium. Other elements like gallium or germanium have much higher effect, so those are interested because with 5% we want to get into the region of 130 to 160. So we need elements like those that are marked here: silicon, boron, germanium, ruthenium is the well-known. But of course, not all elements are suitable. Some of them are toxic, like tellurium. Others, like silicon and germanium, can result in very severe embrittlement, like what I showed you in the beginning. Others, like zirconium, niobium, vanadium, titanium, they are very reactive, and they are not suitable for the investment casting processes that are used in the jewelry industry. So, as you see, there are many elements, but only few possibilities remain. Ruthenium is the most effective, one of the most effective, and boron is also a very interesting element. And boron is interesting because it's a very light element, so you can add only small amounts and get big effects. So therefore, gallium is also an element that is used in platinum, but it's not working as well as in platinum. So here I showed you the phase diagrams of the palladium gallium and the platinum gallium system. The red line shows 95%. And here on the right side, you see the platinum system. You see that the red line is intersecting this line here, and this means there is so-called precipitation hardening. There's small precipitates of an intermetallic compound of gallium and platinum is forming that results in significant hardening. But this does not work that well in palladium because palladium has a higher solubility. So the hardening effect is much less pronounced, and similar effects we have in other elements like indium and tin that are other candidates. Therefore, we were not sure if gallium would be the right choice. So then we started with the simulation, and here I show you such a simulation result. The lines here are for each color stands for a certain chemical element, and this shows the temperature, which is the upper line, and the lower line is the solidification temperature for each element. So this gives us an idea, if we add 5% of each element, how this affects the melting temperature. Our objective was to lower the melting temperature a little bit, because in palladium ruthenium it is very, very narrow, and this is detrimental for casting, because this allows very low feeding. So the metal solidifies all at once as the temperature is reached, and if you have a certain melting range, the metal can flow longer. So we think there are some candidate elements that lower the melting range. There are more elements like rhodium, platinum, gold, silver, and copper. They also have effects on the melting range, but there is the effect on hardness of these elements is very low. Therefore, these elements were of less interest. Then here comes the first list. This is a selection of alloying elements that we prepared. We have palladium, ruthenium as the basis. Then we added cobalt, iron, copper, chromium, and so on. And with these basic binary alloys, we could make mixtures of many alloys that contain, for instance, palladium, ruthenium, and cobalt. And so we could vary the composition quite easily in a very effective way. Then, as I said, boron was an interesting element. Here we added very small amounts, 1 to 5 per mil only. Aluminum was an interesting element. And we also tried things like zirconium, but as I said, this is very reactive. We started with these elements, with these alloys, rolled them, determined some basic properties, and then alloyed them to make ternary alloys. And with these ternary alloys, we did our investment casting trials, with the properties characterization. This is a typical casting tree that we set out. A thin main sprue and then some standard parts like a grid for form filling, a plate for surface characterization, or these rings which are basic rings to mount setting areas for diamonds. Here in this section, we call this one the single gate ring with one gate at the thin section. And this morning you learned that this is not a very good situation because you get shrinkage porosity here. And then we had an opposite ring. We call it the double gate ring, who has sprues at the thicker section. So these are just some examples that allow us to get a principal understanding of the material. We prepared wax trees, mounted them, and used them in centrifugal casting. So this is a model of the tree and the crucible. And here you can see how the parts are mounted. The blue arrow indicates the centrifugal direction. So the parts are mounted on the leading side of the tree, which gives optimum form filling. These are some parameters of crucible materials. It's more, and investment materials. This is more or less the standard selection that is also used for the casting of 950 platinum alloys. Our casting process, we use centrifugal casting machine with these parameters. We overheated the melt to minimum 80 Kelvin over the melting temperature, and our flask temperature was set to 650 degrees, which was an established value for platinum alloys with such setup. We always worked in an evacuated and backfilled argon atmosphere where we could control the oxygen level. Because oxygen is critical, it can be dissolved in platinum alloys, and as you also heard this morning from silver, this can result in gas porosity during solidification. These are all the investigations we made on the different parts, and we also tried some hardening treatments. Now, when we do the process, we have to take care for the process control, and therefore we work with a standard machine, casting machine, but we have some sophisticated characterization methods in line during the process. So for instance, we have a thermal imaging camera which is mounted here and has a view on the melt. This is a typical image at the moment where the melt flows out of the crucible. So we can record the temperature very precisely, and we can identify different situations. So here everything is solid. Then melting starts. Then there is a jump here. This jump is a measurement effect. This happens during the melting process. And then we get the melting temperature, and then there is a kink here in this line, so it's more or less horizontal, and then it increases. So this is the point where melting is completed, and then you have to have a precise temperature control to cast at the right point. Casting is done in standard flasks. Here you see the situation after casting. We used thermocouples that we mounted inside the trees. So here's an example. You see the thermocouple inside the main sprue, and this allows us to measure the heat up of the investment, which can decompose and react. We also learned, thank you Jörg, it was very illustrative. Without your presentation I could not do this one. And then we of course investigated computer tomography and metallography to identify the porosity. Well, the casting result. we assessed several new alloys, interpreted the results, and we did it in a way like this. So this is a typical casting result, the tree after casting, parts cut from the tree. We get the surface quality, form filling, and metallography. And now we found different cases. We assessed set typical parameters like low form filling, medium, and high form filling. Similar for the surface reaction, strong reaction, some residues of investment, and no reaction. And the same with porosity and cracks. Of course, this is useless quality with cracks and many pores. Here we have some porosity, and this one is more or less free of pores. Microstructure. This is a close-up view of the images you just saw, but here we see the grain size. So we see palladium ruthenium has a medium but relatively regular grain size. Elements like tin result in a coarsening and columnar grain size here at the edges, and additions like iron result in a very fine grain size, which is beneficial. Chromium results in cracks. So this gave us a rough estimation, but you see some how the different elements perform, but you see that all elements result in a lowering of hardness. So we have to address this point, and here boron comes in. This diagram shows the effect of the addition of boron to these alloys, and you see that boron has a strong hardening effect. It pushes the hardness from around 100 to around 150, 160 Vickers. Exactly the region where we want to get. In some elements, some alloys it's stronger, the effect. In some it's lower, but it's a general trend. So roughly we can say we gain 60 Vickers hardness points per mil of boron, and we can get to extremely high hardnesses, which of course we don't want to have. We also tested aluminum, and we see the blue curve here, the effect of aluminum content on the hardness. We get a linear trend with 1.5%. We get also in the right range of hardness, and we see that these alloys show a certain age hardening. So we cold rolled the material, then we get a strong increase, and then we annealed it at a certain temperature, and we get a certain difference, and you see that the difference increases with increasing aluminum content. So this is also an interesting result. Then after some more iterations, we came up with 4 compositions that we found are very promising, and we found that the combination of boron and aluminum is quite beneficial, and that we don't need very high additions to get into the desired melting range. Iron is beneficial for grain refinement. Tin is beneficial for increasing the melting range. And so these were 4 compositions which were promising, which met the objectives of the alloys we wanted. However, you have to keep some points in mind. This is I don't go in detail through this list of how to work with these alloys, but you have to keep in mind one point. This is the flask quenching. Usually after casting, you leave the flask for some time in the casting machine to cool down. And this is very important for these palladium alloys. This is demonstrated here. If you put out a flask immediately after casting and quench it, all the parts are broken. So this is, of course, not good. So we have to take care for this point. And even if you quench from 600 degrees, still many parts are broken. If you quench from a lower temperature, there are still the filigree parts are broken. So this means you have to cool these flasks down to room temperature very slowly. This is specifically if you add boron, this is an important point. Now let's compare the new alloy with some other alloys, with white gold and platinum alloys. And here I plotted the density and the yellowness index, which is the color of the alloy. And you see that the color of the palladium is quite similar to the platinum alloys. And these alloys are much whiter than 18-karat white gold alloys. So they don't require any rhodium plating. They have a yellowness index which is below 10. The density of palladium is around 11, 12. So this is much lower than platinum, of course, but also lower than white gold. So we can say the alloys are light, so you can make bulkier or parts with less weight compared to platinum or white gold. They're also bright and don't require rhodium coating. And now this is the hardness diagram. So this was the standard palladium alloy, quite soft, below 120 Vickers. These are some platinum alloys where we have a great variety. Also for white gold, of course, you can have from 120 to over 200 Vickers. And the new palladium alloys are here in the range from medium to hard, so the alloys are strong enough for stone setting. Now let me summarize. We developed new alloys based on 950 palladium ruthenium with addition of iron and tin. But mainly the main effect was the addition of aluminum and boron that allowed us to reach hardnesses of 140 to 160 Vickers. Ductility is comparable to 950 palladium ruthenium. The alloy requires some specific processing. Quenching has to be avoided from casting, and you have to have a good control of your casting process. So companies that can cast platinum successfully should be able to cast these alloys as well. These are the compositions: light, bright, and strong. This is the main summary. But now at the end, let me mention one point. We started the project July 2017, and then it was stopped in autumn 2017 because the palladium price has significantly increased. Here the green line, you see the palladium price was going up since 2016. Platinum price was going down due to requests in the automotive industry. But we see that palladium is very volatile. The palladium price is very volatile because it's mainly an industrial metal and not so much a jewelry metal. So price might come down, and then there could be an interest in such alloys again. So thank you very much for your interest.